What I want to look at here, we've defined reference circle, and hopefully not reference circle, we've defined SHM, and hopefully you've looked at that video first. SHM, the reference circle. I told you that because of the fact that the force is changing with SHM, the equations for velocity and acceleration, sorry, not so much acceleration, but velocity and displacement are going to be a bit tricky. Remember, the equations just with the constant acceleration got a bit tricky with kinematics equations. So it is a little bit tricky, and we use something called a reference circle. So that's our circle, and I'm calling it a reference circle. It is a mathematical tool that's going to enable us to determine these equations and get it right every time. Now, it's all based on a fairly strange thing, which is that if we've got, and you'll see this again in one of my other videos, if we've got a mass bouncing up and down on a spring, and this is the equilibrium point, and it bounces all the way down to that at its extreme, and it starts at that point. If you've got a mass doing that, and it's executing this very complicated movement, where the actual time at which it's at this point, and that point, and that point, it's not linear at all. And it's not even based on a constant acceleration, because we could do that if it was. The acceleration is constantly changing, but it is proportional to displacement. The funny thing is that if we were to have an object going in a circle at a constant velocity, well, it's not a constant velocity, a constant speed, right? Then it's going in a circle. This is bouncing up and down. But the funny thing is, although this is a constant speed, if we project just the vertical component of this thing's position onto a screen, we would get it exactly matching the position of this mass bouncing up and down. So this reference circle becomes a really good tool. It means that I can easily, now, well, not that easily, but I can work out all the components for the displacement, d, the velocity, and the acceleration of this. And the reason I can do that is because I just said that when this little guy goes around in a circle, its vertical component is going to be matching the vertical component of this. So the vertical components of this displacement matches. For its displacement to match, its velocity must match. And if its velocity matches, its acceleration must match. So what we find is that this complicated motion is exactly determined by one component of circular motion, which is really cool. So we can use this now to figure out D, V, and A. Now the thing to remember is that what D are we talking about? We're just talking about the distance from the equilibrium point. That's our D. Our velocity is our velocity at a certain point. And that velocity or acceleration is different at different points. Now with SHM, you can see that it's got its maximum velocity when it's in the middle. All right. When it's at the end, it actually stops. So V equals 0. This is the mass going up and down. And V equals 0 there. In the middle, what about acceleration? Obviously, this is maximum positive displacement, maximum negative. Displacement is 0 because this is from the equilibrium. What about at the ends with the acceleration? Well, that's where it's maximum. It's turning around. All right. It's also related to the force, right? Force equals mass times acceleration. But we actually said that the acceleration, or the force, was maximum at the maximum displacement. So maximum displacement means maximum force means maximum acceleration. So acceleration is maximum there, and acceleration is maximum there. Acceleration has got to be, it's not always in the direction of the movement, right? It's not always in the direction of the movement. But which way is the force? It's always back towards the center. So that's the direction of the acceleration. Now that means that this reference circle, as this little guy goes round and round, then we're saying its velocity at the top is 0. But it's not. Okay, but so at the top, this little guy would project across to the top. We're saying its velocity is 0. Well, we're not. Its velocity is totally horizontal, so its velocity in the vertical direction is 0. When it gets around back to here, or here, its velocity is maximum because it's only now got a velocity in the vertical direction. So this little circle can tell us the displacements, the velocities, the accelerations, just by looking at the motion of this guy going in a circle. Now, we use angles in the circle. So we could start our clock anywhere. We could start our clock when the mass is in the middle, or we could stop it when it's at the top, start it at the top, or start it at the bottom. I like to always start the clock when the oscillating structure is in the middle, at the equilibrium point, which means that if I'm going to measure these distances, and because it's a circle, I measure our distances as angles. So I'll call that theta. So to actually get the distance, I've got an angle because this whole thing's going in a circle. Then my radius of my circle becomes my amplitude for my oscillating object, which in this case is this distance here. That becomes the amplitude, right? How big is its oscillations? So that becomes my A. And if I want to know the distance, say it's maybe halfway around the circle, or halfway from equilibrium to its maximum point, then that just would become A times the sine of whatever that angle is, right? Because the sine of that angle is the vertical distance. So our first equation is going to be that D is equal to the sine of theta. Now, we actually have an object going around at a constant speed, and we learned that that speed, V, equals omega times the radius. This was from our rotational work, but our radius is A. Right? So that's the velocity. What about the angle? If we start our clock at this point 0, equilibrium point 0, then we can also say that theta equals omega t. Okay? Theta is what we're doing here. This just comes from that equation that we had before, which was that omega is equal to theta over t. Right? Omega is my radial velocity, and that stays constant. If I want the actual velocity, I go omega times the radius. That's the linear velocity. If I want the actual number of radians it travels, then I need to go omega times t, because omega actually is number of radians per second. So in these equations, I can write this as A sine omega t. Now when we do that, your omega is always in radians per second. So this has been an introduction to the reference circle. If you look at the reference circle, working out the components and things, the SHM little video on that, I'll work out all those other components. What I want you to understand from this reference circle is the basic idea, and also to realize that even though we just did this reference circle, right, for a mass on a spring bouncing up and down, right, and everything got projected over and it all seemed pretty cool, what really gets to people is the fact that if I now look at a pendulum like this, and it's going backwards and forwards, so in this case A is the distance the pendulum swings, the horizontal distance, not the arc length, then they think they need to use a reference circle that projects down, not across. Now the same reference circle that we used where we project across our vertical components can be used for the pendulum. These same things that we want to work out with our pendulum, at a certain distance away from the equilibrium, I want to know the velocity. I want to know the time it takes to get there. Things like this. That can all be worked out with our reference circle, always done this way with the angle measured like this at that point. because this little bit here, the equilibrium point, is the equilibrium point. The amplitude is the amplitude. And that's this distance here. Right? And when I ask for something like the velocity at that point, or you need to know where that point is, it's the same as this point. So the fact that we've turned it vertical doesn't make any difference. We measure from the time starts from when it's at the equilibrium point, and if you want to work out a displacement from that equilibrium point, then the equation we found was just A sine omega t. Right? That's our omega. Sorry, not our omega, that's our angle, which is equal to omega 2. So the reference circle that we use here works for all SHM, and we always are talking in terms of the angle being measured from the equilibrium point. So it doesn't matter whether we've got a pendulum going backwards and forwards, or a spring going backwards and forwards, or a spring going up and down. This tool works for them all.